Hi, well, it's been a while since I've done a video on Young and Freedman's University Physics, but let's go ahead and start the pilgrimage through chapter 22, which is on Gauss's law. Gauss was a genius who lived in the late 1700s, and I'm very jealous of how smart he is, but at least I'm alive. I guess that's not a nice thing to say. Not important. Let's move on to the first section of this chapter, which is charge and electric flux. Charge and electric flux. Chapter 22 of Young and Freedman's University Physics. All right, so the previous chapter, we did some pretty complex math, or at least it was involved, to try to figure out, just basically using Coulomb's law, how, the inverse square relationship, adding up the charges and everything. What Gauss's law allows us to do is, and by the way, James Clerk Maxwell came up with this, in the late 1800s. But Gauss's law allows us to take the complex calculations of the previous chapter and simplify them by putting them in an imaginary box. And what happens is that you have the charge at a distance is inversely proportional to the radius square, right? But what happens is, as the box gets bigger, it cancels out the r squared. And so it doesn't really matter. We don't have to do as complex math because we're looking at everything as if it's some sort of a imaginary box. And it doesn't have to be a box. It could be an imaginary sphere, imaginary cone. It doesn't really matter, although I think a box is pretty easy. But we're only measuring what's happening at the surface of the imaginary box. So this section is on something called electric flux. What is electric flux? Well, electric flux is the net flow of that charge force at the surface of that imaginary kind of box. And again, it doesn't matter how big the box is because it cancels out the r squared of the charge. And so by it's a trick, right? It's a trick. By looking only at the imaginary surface, we can measure electric flux as the net flow of that force at the surface. And these are some definitions. If the charge going into the box and the charge coming out of the box, by convention we say that negative charges are charges that end in the charge or in the box. Positive charges are charges that come out of the box. But if the net inward and outward flow is zero, then the flux at the surface is zero. If the net flow of the charge is outward from the box, we say that its flux is positive. And if the net flow of the charge is inward in the box, inside the box, we say that the flux is negative. Just that's somewhat conventional by the way it's been defined historically. All right, so we can draw lines of force to picture this. It helps us because we're visual people. Many of us are. Humans tend to, if we can see it, it makes more sense to us. So when you're drawing lines of force, the more lines you draw, that symbolizes a greater magnitude of charge. So if you have two lines, by convention, that means it's a double the charge as if you only had one line. Of course, we're not going to be real precise on these sorts of things. It's more of an impression or an intuition that we're giving. Net of electric flux through the surface of the box is directly proportional to the magnitude of the charge. So even though the r squared of the previous chapter of Coulomb's law cancels out, the charge part, which was in the numerator in the previous chapter, in the numerator of Coulomb's law, the net electric flux is going to be directly proportional to the magnitude of the charge inside the box. Again, the size of the imaginary box doesn't matter. Size doesn't matter. Okay, so what is electric flux? You're talking about electric flux. What is it? Well, for each face of the box, we are going to define electric flux, and now we don't necessarily have to understand what's going on here, but we're going to define the electric flux as the average perpendicular component of the force, electric force, and the area that it's coming out of, or say the area of that face of the box. So if we take each face of the box and we take the average perpendicular component of that electric force coming out of the box, multiplying those two together, that's going to give us what we call the electric flux. We're going to make this more precisely mathematical in a later part of the chapter. And so then you add up that result for all the faces of the box. And so for each face of the box, and there are what, 1, 2, 3, 4, 5, 6 faces of the box, of a box, you're going to multiply the average perpendicular component coming out of the box, electric force, by the area of the face, and then add up all the faces of the box. So this is a less precise way of thinking of Gauss's law, but basically the sign of the enclosed charge is going to tell us whether the net flux is outward facing or inward facing. If it's outward, it's positive. If it's inward, it's negative through the surface. So the sign of the charge tells us the net inward or outward flux. And then the charges outside the box, they don't give us any net flux because they come in and out of the box, and going in, they're negative, and coming out, they're positive, and they cancel each other out. So only charges that are inside the box count. And then the net electric flux is going to be proportional to the net enclosed charge. And there you have it. That is Gauss's law in simple terms. Just to begin to get a sense of Gauss's law from a qualitative standpoint, we are going to look at it from a more precise mathematical perspective in a later section in the chapter. But again, this is probably the biggest deal of this video, other than what is a positive, what is a negative. That's all very easy. But we're going to multiply the average perpendicular component of the electric force coming out times the area of the face, add up all the faces, and that's going to give us the total electric flux. Okay, hold that thought, because there's more in this chapter. We're going to go mathematical soon enough.